Okay, so now we're going to see an example of two random variables which are not independent of one another. Okay, so this is the problem. So the abstract probability space is that we now have a sphere of points that we are choosing. A sphere like this. So we have the unit sphere on R2. So this is the unit sphere, so it's at radius 1. Now, we can ascribe to this, so it's the unit sphere of radius 1, so all the points in this unit sphere are in our sample space, and the problem is that you're going to pick a point in the unit sphere randomly. So each point is uniformly likely to be picked. So basically, when we take the joint PDF, what we're going to get, we want it to be uniform. We want basically, remember, if we look at PDFs, they are effectively like the infinitesimal version of probability. So we want each point to be uniformly likely to be picked. Okay, so firstly, let's set up some random variables. Let's set up a random variable x, which is going to ascribe you your x coordinates. So it's going to ascribe you a number between -1 and 1. So if you're over here, like here on the actual edge of here, you'll be ascribed -1. If you are here, if you're anywhere along the y-axis, you're going to be ascribed the value 0, and if you're over here, you're going to be ascribed the value 1. So it's just going to ascribe you your x coordinate. Similarly, we can make the random variable y, which is just going to ascribe you your y coordinates, and again, this can take on any value from -1 to 1. So if you are right down here, you will be ascribed the value -1. If you are anywhere along the x-axis, you're going to be ascribed the value 0, and if you're right at the top, you're going to be ascribed the value 1 again. Okay, so it's going to ascribe to every point a y coordinate, and this one's going to ascribe to every point an x coordinate. So every point has a unique x and y value. Okay, so we want the joint distribution of x and y. So the way you can think about that is it's the probability that you are at it's the probability density that you're at a unique point. So take any unique point in this sphere, and you can't ascribe a probability to it because its probability is 0, but you can ascribe a probability density to it, i.e. if you take some tiny little delta x and some tiny little delta y, if you multiply those by it, so if we've got some tiny little square in there, it will give you the probability that you are, it will roughly give you the probability that you're in that square. That's why it's called the probability density function, because you have to multiply it by an area or a volume or whatever to turn it into an actual probability. Okay, so that's the way we can roughly think about that. So if I take any little square wherever if you go wherever you want in here, take a little square, I want the probability to if that square is infinitesimal, I want that probability that you're in that square to be the same wherever you are. I don't want that to depend on where you are. Otherwise, it would be more likely that you'd pick a point in a little square at one place than in the other place. So I want this to equal some constant value, basically. Okay, and then all I need to do is divide through by this delta x and delta y, which were constants wherever you went. They were very small constants, but they were just constants. So I get basically that this needs to equal some other constant. Let's call it k. Right, so we want the joint PDF to be equal to a constant, at least on the circle, and we want it to be equal to 0 everywhere else. Now, that means we know that if we integrate over the entire R of R2, so I've just put over all of R2, the joint PDF of x and y as a function of x and y, dx dy, we want that to equal 1, because of course the probability of the events that absolutely everything happens, anything happens really, should be equal to 1. So if we put in a constant there, we get that we want the integral of the constant dx dy over all of R2 to be equal to 1. Oh, but I've made a mistake there, because it's not equal to a constant over all of R2, it's equal to this constant over the sphere, and then 0 everywhere else. But if you integrate 0 over everywhere else, then it's just going to be equal to 0. So we only really need to integrate over the region which we'll call D for disk, so this disk here. Okay, now if you integrate a constant over a region, all it gives you is the constant times the area of this region, which I'll call A. So the constant times the area of the region needs to equal 1. Now what is the area of the unit disk? Well, the area of a circle is given by pi r squared. The radius is 1, so it's pi times 1 squared, which is just equal to pi. Now, that gives us that k times pi needs to equal 1, which tells us that k is equal to 1 divided by pi. Okay, so our our joint probability density function as a function of x and y is given by 1 over pi if you're an element of the unit disk, so if x and y is an element of the disk, and it's 0 if the ordered pair x and y is not an element of the disk. Okay, so that's our PDF. Now, what we want to calculate is the marginals, and then we want to show that the marginals are not, well, if you multiply the marginals together, you do not get back the joint PDF, because remember, if they're going to be independent, we want the joint PDF to be equal to the marginals multiplied by one another. So basically, I've said that this is not going to be independent, so if we want to prove it's not independent, we need to prove that if we multiply the marginals together, they're not going to give the joint PDF. Okay, so let's get the marginals, basically. So what do the marginals mean? Just time for a bit of a recap. So if I get my picture back, because I don't want to have to... In fact, I'll draw it again. So, our abstract probability space is this unit disk here. So this is the unit disk, D, and you're picking any point from within there. We have two random variables, a random variable big X and a random variable big Y, which describes your X coordinate, which is from -1 to 1, and the big Y ascribes your Y coordinate, which is again -1 to 1. Okay, so what we can ask is, now, okay, I don't care about the random variable y, I'm just going to view this as a probability space with the random variable x on, and I want to know what is the PDF of this random variable x. That is what we mean by the marginal distribution as a function of marginal PDF of the random variable x as a function of little x. So what is the probability that you have, the probability density that you have a little, that you are at the value x? Well, if we think about timesing this by some tiny little delta x, that tells us the probability that you are within an interval. So if we have -1 to 1, these are all the values that x can take on. So if x is here, then if we multiply it by some tiny little delta x, if we multiply the PDF by the tiny little delta x, that tells us the probability you're going to be in there. Now, what is the probability that you're going to be in there? Well, it's going to be, if we think about it back here, it's going to be the probability that you're in this entire strip here, because all of these values will be given that same x value. It will be given an x value within this strip over here. So that's going to equal it's going to equal the sum of the joint PDF. So the joint PDF x and y times. You're going to have to times it by delta x, and you're going to times it by delta y, and then sum it over all values that y can take on. But of course, we're letting delta y go to get infinitesimally small, so this will become the integral over all those values of y, dy, and then we'll just cancel this delta x, and we'll get that the marginal distribution, the probability density that it's in a tiny interval delta x, is equal to the integral of the joint probability density function over that value of x. Okay, so the integral, now we need to work out what are these limits of integration, and this is the crux of the problem. This is why it's not going to be independent. This is why your x value does affect your y value, because if I get an x value that is, say, 1, if I take the most extreme example, if I get the x value that's 1, then your y value is set. Y is equal to 0. There is no possibility. Whereas if I get an x is equal to 0, it can take on any value between -1 and 1. So clearly, y is influenced by x. So y and x cannot be independent. Okay, so we need to work out what are these limits of integration. So what are we integrating from and to? So we're integrating from this value down here to this value up here. Now, what are those values? Well, the value of y is given by this top curve, is given by, so if we split it into two curves, basically, this top curve here, this bit, is given by the formula y is equal to the square root of 1 minus x squared, and the bottom curve is given by the negative of that, so the -1 minus x squared. So y bottom, I'll call that. Okay, so the value of y at x at the top is equal to just the square root of 1 minus x squared, and the value of y at the bottom is just equal to negative the square root of 1 minus x squared. Okay, now we stick in our PDF on this disk, which is 1 over pi, and integrate that dy. Okay, so if you integrate a constant, you get by the second fundamental theorem of calculus, this is just 1 over pi times y evaluated between 1 minus x squared, and the lower limit is the negative 1 minus the square root of x squared. Okay, and this is equal to 1 over pi, sorry, not 1 over 2, 1 over pi times 1 minus x squared minus 1 over pi times minus 1 over x, 1 minus x squared rather. Okay, and this gives us 2 over pi times the square root of 1 minus x squared. Okay, so now what we'll do is calculate the marginal for y, y random variable, and it's exactly the same calculation, but we'll go through it again to recapture the finer points. Okay, so if we have our abstract probability space and we have this unit disk again. Okay, so here we are. And we are now just viewing y as being the only random variable. So we're only interested in y now, and this is ascribing to every outcome in this probability space a number between negative 1 and 1. So it's ascribing its y coordinate. Okay, so if we want the probability density of the y distribution as a function of y, if we times that by a tiny little value, delta y, then if we think about our interval here, this is 1, this is minus 1, and this is 0, then we have some value y here. And if we multiply it by a tiny little delta y, it's the probability that you are within that interval. Now, all the points that are going to be mapped onto that interval are these points here. So that is equal. So if we want to work out what this probability is, it's going to be equal to the sum over all the values that x can take on of the joint probability distribution, which is the probability that it's in a tiny, well, you have to multiply it by delta x, delta y, which is the probability that it's in a tiny little region, and then we let delta y get infinitesimally small so that we can make this really fine, and this becomes the integral, sorry, delta x we let get really small, and this becomes the integral over all values of x in there of the joint probability distribution xy dx times this delta y. And the delta y will just then cancel with our delta y here, basically. And you'll get that the marginal probability distribution of y as a function of little y is equal to this integral. Now, we just need to work out what the limits of integration are now. And again, the limit of integration over here is going to be the square root of 1 minus y squared in this case, and the limit of integration down here is going to be negative 1 minus y squared. So the way that you get that is this curve is overall given by x squared plus y squared is equal to 1. All the points on this circle satisfy that property. Now, if we view if we view x being a function of y, then we're going to have to split this up into two parts. We're going to have to split it up into this part here. So we're going to have to split it up into this part, the parts with a positive value of x, and we're going to have to split it into this part here. Okay, so the positive part you can view as being, well, it's going to be equal to, if you bring the x over, if you bring the y over here, then you get x squared is equal to 1 minus y squared, and then it gives you x is equal to plus or minus the square root of 1 minus y squared. So if you take a value of y, there are 2 points corresponding. One is the positive point and one is the negative point. So the positive point corresponds to the square root of 1 minus y squared, and the negative point over here corresponds to the negative of 1 minus y squared. So if you were to view this as a function, you could view it as the square root of 1 minus y squared would give you this blue function, and the negative of that would give you the pink function. Okay, so if we want to perform this integral, then we have to substitute in what the PDF is on the disk, and that's 1 over pi. And again, you integrate 1 over pi, and by the second fundamental theorem of calculus, you get x over pi, and then you're evaluating it between the square root of 1 minus y squared and negative 1 minus y squared, and this again gives you 2 over pi times the square root of 1 minus y squared. Okay, so we have these two marginal distributions, and you can see instantly that if we multiply this one with this one up here, they are not going to give you just 1 over pi. It's not going to cancel in some beautiful algebraic way. It's just not going to work. So the two marginal distributions are not independent, and that fits with our intuition that they cannot possibly be independent. Okay, so now I'm just going to use this example to do some conditional probability as well. So let's work out what the conditional probabilities are now that we've calculated the marginals. So let's work out what the conditional probability of x given the value of y as a function of little x and little y is. So intuitively what this is it's saying we have this disk over here. So this is our abstract probability space, and again we have some random variable x which ascribes the x coordinate, and it's giving you a value between -1 and 1, and we have some random variable y which is describing you the y coordinate and is giving you a value between -1 and 1. Okay, so if we want to know what is the conditional probability of getting a value little x given that you've got a value of y, little y, what you are saying is, okay, we've fixed a value of y, so this is our little value of y. Now, x can still vary, x can take on any of these values along here. What I now want to know is what is the probability that x is well, what is the probability density, because of course the probability is 0. What is the probability density that x is equal to any of these? Okay, so that is equal to, so if you want to turn it into a probability, of course, you can multiply it by some tiny little delta x. So we can say multiply this by a tiny little delta x, and that will give you the probability that it's within a tiny little region delta x on there. Now, this is equal to the probability of being in a tiny little box on here. So the joint probability distribution density function times delta x delta y gives you the probability of being in that tiny little box down there, and then if we divide that by the probability of being along this line in the first place, of being along this tiny little whatever that shape is, a rectangle along here. So the probability of being along a tiny little rectangle here is the marginal distribution of y as a function of y times delta y. So basically what I've said is the probability that you take on a value x, the probability that you're in this tiny little length region delta x here is the probability that you're in that tiny little box here, divided by the probability that you're overall in this rectangle here. Okay, so the delta y's cancel and the delta x is cancelled to give you that the joint PDF, the conditional PDF of x as a function given y is equal to the joint PDF of x and y as a function of little x and little y divided by the marginal PDF of y as a function of little y. Now, we know that the joint PDF is just equal to 1 over pi on the disk, and we know that the marginal PDF of y as a function of little y is given by this formula over here, is it not? Yes, 2 pi over the square root of, times the square root rather, of 1 minus y squared. Multiply top and bottom by pi, and we get that this is 1 over 2 times the square root of 1 minus y squared. Does that look right? Okay, yes. That's saying basically that it does not depend on x, you'll notice. So if you pick a value of y, then after that it's uniformly distributed. Your x values are completely uniform. The probability density that your certain x value is completely uniform, i.e. none of the x values are preferred to any of the others, is what that's saying. So that's nice. And similarly, if we calculate the conditional probability of y, given that x is known as a function of x and y, okay, well what that says is pick a value of x, and what we want to know is what's the probability density of the values of y that can still vary. So this is given by the joint probability density function as a function of x and y divided by the marginal probability distribution of x as a function of x. So this is just 1 over pi divided by this marginal distribution, which is 2 over pi times the square root of 1 minus x squared, and this just gives us 1 over 2 times the square root of 1 minus x squared. So you'll notice that as you go off towards the more extreme points, away from the centre, the probability density gets higher and higher, and that's because the total number of possibilities, if you get, so for instance, if we look at this one here, the total number of possibilities of values for y goes down as x approaches 1. So as x approaches 1, this is going to go to 0, and the probability density is going to get bigger and bigger and bigger and bigger and bigger, because the number of possibilities is getting smaller and smaller and smaller and smaller and smaller. So as you make x more extreme, as you fix x being more extreme, the probability density is going to have to, of being at a specific point, is going to have to go up, because there are fewer points that it can that y can take on. There are fewer values that y can take on. Okay, so that's all for this video.